All right, so central limit theorem and confidence intervals. This is all building on this idea or on these ideas of the standard error of the mean, the sampling distribution of means, and just more broadly, this idea of the relationship between samples and populations. So, central limit theorem. Previously, we discussed a scenario with 100 samples of 200 people per sample. Larger populations bring larger samples. So this is where central limit theorem comes into play. Central limit theorem states that the distribution of sample means, so how sample means are distributed, will approach a normal distribution as the number of samples approaches infinity. So to kind of boil this down, we're saying the more samples that we take, the closer we get to a normal distribution. Okay. So now we'll kind of turn our attention to the mean of the distribution of sample means, which we've discussed as the mean of means. I joked about this as the boss mean. This is the expected value. So the average of all sample means is equal to the population mean. Okay. Remember that in an example when we first started talking about sampling error, I showed you a series of test scores as a population. And then next to that population of test scores, I showed you an example of what happens when you draw, one sample from that population and then take the average. A second sample, you take that average. Third sample, you take that average. Those averages of each of those samples are not necessarily and are very statistically unlikely going to be the same as the population mean. However, if you take all of those means and you average them, then you are going to get the population mean. So this mean value is called the expected value. And this relates to this idea of confidence intervals because we're talking about this idea of population mean. The goal that we are trying to figure out is how closely can we get to ensuring that our data is actually reflective of the population, that our sample data. So confidence intervals are this idea of a range of confidence intervals are the ranges in which the true value of the population will lie with a high probability, right? High probability in this case refers to the probability with which a population value should lie in the confidence interval range. When I'm talking about a confidence interval range, I want you to think of it as a window. Okay, I'm holding my hands up to represent that this idea of a range means that we're going to have a value on the low end of our confidence interval and we're going to have a value on the high end of our confidence interval. And what we're ultimately trying to say is that with high probability, somewhere in this window, the true population mean exists. So as researchers, we define which levels of confidence that we want to work with. However, the most common confidence intervals to work with, particularly in social science research, is going to be 95 and 99%. And those are the two that we are going to focus on in our class. When it comes to doing things by hand, we're largely going to be focused on 95%. And then when we move into SPSS, I'll show you all how to change the settings in SPSS such that you can adjust the confidence interval from 95 to 99, but even within SPSS we will largely be leaving the default of 95%. If a confidence level of 95% is given, then that means, and this relates to the way that we are going to create our concluding statements, that we can be 95% sure that the true population value lies within the confidence interval. As I mentioned previously, I know sometimes this information can be a bit overwhelming. Stick with it, okay? It's going to make sense, I promise. All right, so I'm going to show you an example of calculating a confidence interval, all right? And so we're going to kind of revisit this idea of the IQ test. So I'm going to give you a scenario. So let's say a principal at a private school wants to estimate the mean IQ of her student body without testing all 1,000 students. So her population is 1,000 students, but she doesn't have the bandwidth, the excuse me, whatever bandwidth that she's not able to test all 1,000 students. Instead, she selects 25 students at random. she finds that the mean for her sample is 105. So of the 25 students that she surveyed, their average IQ is 105. This means the mean, the sample mean is, or rather, the mean is from a sample and not the entire population. And so she cannot be sure that the mean is actually representative of the population. So we're ultimately saying, while we pulled a sample of 25 students, we don't know for certain that the 25 students who have a mean IQ of 105 is exactly the same as our our population mean would be. We're ultimately asking the question, is the IQ, the mean IQ of all 1,000 students, is that 105? We don't know, right? We don't know. So part two of this IQ test is, got to give you some more information. So let's say we also know that the standard deviation for IQ tests is 15 based on previous data. Using the standard deviation and sample size, we can calculate the standard error. All right. So that is the extent to which the sample mean diverges from the population mean. So given all the information that I provided to you, we are able to calculate the standard error of the mean. And I'm saying that to you because that's important. Okay. In order to calculate the standard error of the mean, we're going to take the standard deviation divided by the square root of n. So remember that our standard deviation is 15 based on the information provided to you in this prompt. On the previous slide, I shared with you that there are 25 students in the sample. We have, 15 divided by the square root of 25. So 15 divided by 5, we have a standard error of 3.